LeetCode Problem 16. 3 Sum. Closest tackles a real-world pattern, finding optimal combinations under pressure. Think anomaly detection or fast-paced trading, where time and precision matter. At first, a brute force triple loop feels natural, but once performance hits, brute force crashes hard. So how do we slice through the noise and land on the closest sum, fast? Let's dive in. We'll kick things off with brute force. That means checking every single triplet to see which one hugs the target the tightest. Not smart, but very thorough. First, we set a baseline using the sum of the first 3 numbers. This gives us something to measure all future triplets against. We also store the array's length, so we're not recalculating at every loop, just makes things smoother. Time to anchor our first loop. We fix the first element of the triplet, stopping 2 spots before the end since we need room for 2 more numbers. Next, we fix the second element. We start just after the first to keep our triplet ordered and avoid repeats. Now we add the third loop. It picks the final number, always coming after the first 2 to keep combinations unique. With all 3 elements locked in, we compute their sum, ready to see how close it gets to the target. If this triplet beats our current best, that is, it's closer to the target, we update our result to track it. After grinding through every triplet, we drop the one with the closest sum to the target. Brute force runs in big O of n cubed. For 500 numbers, that's 125 million checks. Like inspecting each duck in a 500 duck parade 3 times. Space is big O of 1 since we don't store extras. Just watch out for integer overflows with huge values. But brute force still wastes cycles. Can we do better by building on what we've already seen instead of rechecking every combo? Let's swim toward that next optimization. We start again by grabbing the array length and setting our closest guess to the sum of the first 3 elements. Now we loop through the array, fixing the first number. We'll track everything we have seen so far in a set, giving us quick lookup for smarter triplet building. Then we scan ahead with a second loop, pairing the fixed number with each next number to form a base for our triplet. For each pair, we figure out the complement, the number we'd need to hit the target exactly. We check the scene set to see if any past number, when paired with the current 2, gets us closer to the target. Each time we build a new triplet, we compare its sum to our current best. If it's better, we update our result. After checking all the triplets with this pair, we toss the current number into the scene set for future use. Once we've tried every possible triplet with this method, we return the closest one we found. This trimmed down version runs in big O of n squared. That's just 250,000 checks for 500 items. Space is big O of n thanks to the set, but it's a worthy trade-off to dodge millions of extra computations. Still, we're repeating effort in checking pairs. What if we sort the array and use 2 pointers to zip through combinations more efficiently? Let's level up with that. Step 1. Copy and sort the array. Sorting paves the way for the 2-pointer technique, which avoids the mess of triple loops. Then we prime our closest sum with the first 3 numbers, a quick baseline for comparison. We loop through the array, locking in 1 number at a time as our anchor for the triplet. For each anchor, we place 2 pointers, one just after it and one at the end, letting us scan combinations in linear time. As we go, we compute the sum of the current triplet. That's our candidate to check against the best so far. If it's a better match for the target, we record it as our new closest sum. To move the pointers, if our sum is too small, we nudge the left one up. If it's too big, we pull the right one down. After we've explored all pointer combinations for each anchor, we land on the closest sum and wrap up. This optimized strategy is also big O of n squared, but it's cleaner, skips hashing, and avoids redundant checks. Space is big O of n for the sorted copy. In interviews or production, this method shines for its predictability and efficiency. We began with brute force, big O of n cubed, slow and heavy, like waddling through a duck pond blindfolded. Then we hashed our way to something smarter. But the real win? The 2-pointer trick. Still big O of n squared, but way more practical. It cuts waste, respects order, and keeps memory low. This isn't just the cleanest fix. It's what you'd reach for in a real system. Whether you're cleaning real-time data, filtering signals, or prepping for a top-tier interview, this kind of clarity and control is what sets you apart. Now it's your move. Try all three methods yourself and think about where else the two-pointer strategy might glide you ahead. Stay curious, keep quacking, and chase that next optimization.